extremely pleased today to be able to introduce to you Professor Flavio Fenton from Georgia Tech University. And I know Flavio for a long time now. We've collaborated for about 10 years on and off. And we're part of the same cybercardia project, which is known as CPS Frontier Project. Professor Glenn and Kim are also on this project. And Flavio is a renowned physicist or biophysicist, having developed one of the iconic cardiac cell models, 4-variable cardiac cell models, called the minimal model, or referred to as a minimal model. He's also one of the lead authors on a recent Nature paper about the LEAP technology for low energy treatments of fibrillation in the heart. It's quite an advance. And today, Flavio is going to talk to us about a very interesting topic, high-performance computing and heart simulations with direct clinical applications. So again, I'm very pleased to have Flavio here today.
Thanks, Scott. Thanks for the invitation. Thank you. Thanks, hi, everybody. Thanks for having me. It's a pleasure to be here at Stony Brook. And so I want to tell you a little bit about just some stuff that we do in my lab. We work a little bit with try to do simulations of cardiac tissue, which requires some high-performance computing. So I'll tell you a little bit of why is that and why I want to study the heart and what are the challenges. In my lab, in the lab where I work, I would like to do anything that oscillates. Anything that oscillates and has complex dynamics we like. So let me start just by showing you an example of a system. Well, in the outlet first, I'll try to evaluate oscillating systems. Let's see if it stops. Okay. So I'll tell you a little bit about oscillating systems in general, just to start for what the heart, and then how spiral waves are a solution of oscillating systems that are coupled in space, and then how they relate to the heart. I don't think I'll have too much time to talk about bifurcations, but I'll tell you some of the dynamics that happens in 2D and 3D. And then I'll finish talking a little bit about what Scott mentioned about the method to defibrillate that actually was delivered first. We studied using numerical simulations, then in vivo, and then finally in vitro. And so anyway, just to start, to make the point that complex systems don't necessarily need to be complex. A very simple system can have very complicated dynamics, very complex dynamics in the sense of nonlinearity. So let me start with this very simple system that I gave it to one of my undergrads, and we're studying it. It's very nice. So you take a candle, you cut it from both sides so you can actually see the wick on both sides, and you balance it in the center of the mass. You take the center of mass, you balance it there, and you burn it from both ends. So what do you expect to happen? It's going to start dripping, right? But then what there will be any motion. Originally it's in a steady, it's a fixed point, but is the fixed point will be stable or unstable?
So this is an unstable fixed point.
This is an unstable because it's not going to drip exactly the same way, right? And there's little things that is going to drip one a little bit more than the other one. So once one drips a little bit more than the other one, what's going to happen to my it's going to what happen? It'll tilt a little bit, right? It's going to tilt. And the flame is going to be always, because of gravity, is going to be always perpendicular, right, to the ground. So it's going to be now, it's tilted this way. So the heavier part that is here is going to be touching more flame than the light one. So the heavier one is going to start melting faster than the light one. So what is going to happen? It's going to switch, right? So now, and then the heavier one now is going to be, so it's basically going to become an oscillator. So it's going to start oscillating. And it's actually a game that has been mentioned back in France from last century. So this is an example. You can just do it in your house. This is one of the first examples we did in the lab. So you see it will start oscillating little by little. And starts oscillating more. But eventually, because there's a little bit of friction, it damps. It's a damp oscillator. So eventually just gets to a fixed point of oscillation, not fixed point of, but it will start growing the oscillation, and eventually will saturate, right? But if you look at the equations of motion, it's very simple to write. You can just basically torsion and torque, a torque, and then the change of angle. So you have angular velocity, the angle changing, and then you have a change of mass and a change of radius. But those two are related, right? Because if it's a homogeneous system, then the mass and the radius will be related. So you actually end up having just three equations. So three equations. When you have three equations of motion, then in principle you can have chaos. So we're thinking this system could have chaos in principle, but we didn't observe it. So the reason that it was not observed is because there's some friction that damps the system. So you have this minus WK, KW that fricks you. So one of my undergrads then basically decided, okay, let's put a ball bearing to really decrease the friction. So she did a little 3D printer to make easier to put the to stick to two candles and a bar bearing, so then you're actually no friction. And then when we did it, then actually you can observe that there's very complex dynamics. So here we look at this point here. So it was high here, so it's going to oscillate. It goes up and down there. So it oscillates to the almost same peak. Now it's coming back. But now in this case, it's tilting a little bit too high, and it's going to go actually over. So now we're going over, right? And then, but it won't go over again, right? Then it goes here, and then comes back again. So it's oscillating, but it can go up, come back, and it can go back again. So if you measure that as function, if you put this one as function of the amplitude, then you see actually very complex dynamics. So actually it does show complex dynamics. Now, the question is it chaotic or not? So there are two things that define a chaotic system. One, you have periodic orbits, and the other one, you have a Lyapunov exponent greater than 1. So we can write the trajectory in space. So because we know there are three dynamic space, we can actually use, there's a time delay system that you can use. You consider the first 3 time delays. You can plot them in space, and you can find where they're actually at some point when they are 0. That means that are close to periodic orbits. So you find actually a few periodic orbits in the system. So let me show you an example of a periodic orbit. Periodic orbits in in chaotic systems is that it gets close to a trajectory that is going to be repetitive, but eventually comes out of it. So it's not, for a little bit amount of time they're repetitive or close to repetitive, but then they come out of it. So here is an example. You can see this a little later because there's more flame here. You see a little burn there. But they're started almost about the same. This is the trajectory. So in this case, they come from different dynamics and then up with different dynamics, but for a small amount of time, they actually have the same dynamics. Let's see if I can play them at the same time. There's a little bit delay there. You're tracking the position of that dot, yeah. So one next time, one a little bit, one after the other one, but exactly. But basically, for that amount of time, they were actually very similar, right? They were very similar. So that actually shows that there were actually some periodic orbits. We calculate the Lyapunov exponent. There are some methods to do that, and it turns out that it's positive, which is actually one of the things that measure that is complex. So anyway, it's just a simple example. I just wanted to say of a show one simple cell that can oscillate, but then I have actually extra dynamics that become complex, that is chaotic. So now you can imagine the heart as a cell. Just, I mean, it's an oscillator, but can also have these complicated dynamics. And you can have it from the single cell. Single cells can have complicated dynamics, but also once emerging, there's emerging behavior that can happen that creates new dynamics that is like that. So what happens is that once you have in tissue, when you collect oscillators, when you connect them in tissue, you can have waves. And waves, another solution of waves is spiral waves. So these spiral waves can actually form any time you have a system that oscillates, but you can couple, you can also have spiral waves. So to show you an example how easy it is to do that, we have done this in Georgia Tech with students. So we can put about 600 students in a grid, and each student can oscillate. So you can have basically the oscillation is to put your hands up and down. The coupling is coupling by diffusion. If anybody is excited of your neighbors, then you get excited. That is the rule, right? So it's basically like the wave in the stadiums. So it's the same way. But now we give them an initial condition that actually we start just only with part of the tissue excited, but not the other one. So then it produces a wave that I know you can see here, the hands up. You can see that he's putting the hands up and down. So you can see the spiral wave forming. So it's actually a clear solution of these systems of the that oscillate. Now let me show you a little bit. If you speed up this movie a little faster, it's easier to see. Let me go. Now this looks funny because it's speeded up, but it's a little easier to see the spiral wave. It's another year later on, we did it again. All right, so I hope I convinced you that it's very easy to do a solution of in a way with spiral waves. Now, one thing that also happens is that once you have a spiral wave, sometimes you can destabilize the spiral wave and break it into multiple waves. And when you have multiple waves, they are always with the same frequency but out of phase. So now the system becomes chaotic. So in this case, every now and then, some of the students that are not paying attention, they see the wave and then they react a little too late. Or some are too anticipated, they see it coming, they activate too soon. So there are a little bit of decoupling. So every now and then you can actually have breakup. So here's the spiral wave forming. Now you see a couple of kids that got excited a little too soon. And now they disorganize the whole system, right? So now it's all completely chaotic. Right? So it takes very little to destabilize the spiral wave and make a system chaotic. So this is one of the source emerging behaviors that you see from a system that oscillates. You couple in space, you can go waves, or you can spiral waves, and you can decouple into chaotic systems. So the same thing happens to any system that has oscillations. So spiral waves can happen to us. There are some not dangerous.
But they're not desirable.
They're not desirable, yes, yeah. So they're not desirable. Well, some may be, actually. There's a little. One example is erythema anularia. This is an irritation. It's similar to what you have a ringworm, but in this case, the excitation actually has a refractory period. So you can actually, these activations of rash, they actually can turn and can produce spiral waves. You can have in the tongue. In the tongue, there's also like your film in the tongue can actually get a little bit. Some people, when they bite themselves, they can produce this wave that propagates, or when they eat, there's people that are sensitive to some acid in some fruits, they can initiate that. So you can have waves that propagate, and sometimes they can break and produce spiral waves. There's sometimes in the uterus, actually, there's having spiral waves, so sometimes probably those are maybe desirables. When people have migraines, I think to talk about a depression of the depression waves that actually form spiral waves that actually drive this migraine. The worst case is when they happen in the heart. So the heart, these spiral waves can be from electrical signals. So the heart, the way it works is you have the four chambers. You have the atria, the receiving chambers, the ventricle chambers in the bottom. And you have the atria contracting and then the ventricle contracting. The contraction is driven by an electrical signal. So the electrical signal is the one that produces the contraction. So you have the P wave from the, so you can measure with the ECG. You have the P wave for the contraction of the atria, the QRS for the activation of the ventricles, and the T wave for the deactivation of the ventricles. So you can consider that as a wave that propagates through it and makes it contract. But when you have a spiral wave that develops, then that's dangerous, because you have the normal pacemaker, normal position like a wave. This one? Yeah. Well, that's a numerical simulation. So this one I just took a heart, I took a picture, so I make a 3D, and then I put a quick simulation on top of it. So this one is, so you can see just the normal activation as a wave that propagates through the heart. When a spiral wave forms in the heart, it turns out that the rotation of the spiral wave is faster than the pacemaker period. So they take control over the heart. So when you have electrical waves in excitable systems, when you have two waves that collide, it's not like water waves that they actually bond and then continue and pass. Because you have refractory periods, when two waves collide, they annihilate. So when you have two systems, you have the natural pacemaker and a spiral wave rotating with a faster frequency, then it's going to take over control over the natural pacemaker. And it's going to take control and then make the heart contract faster. And when you see it on the ECG, that gives you this normal fast tachycardia. Okay? And you can do a simulation of spiral wave in the heart. I showed you that it's very simple. Very often in real tissue, when you produce a spiral wave, then it just breaks. And that in reality, when you have a spiral wave that breaks in the ventricle, that produces fibrillation. That the heart is now actually not contracting autonomous. So you have little sections of the heart contracting at different phases. So this is an example with a pig heart. It's not going to play. Well, this is the one from fibrillation. So you see it now. Actually, the spiral wave is just shivering. So that produces the fibrillation in the heart. So why do we want to study cardiac dynamics and fibrillation in particular? Well, heart disease is the #1 cause of death in the United States. It's as many as the next two causes of cause of death combined. So it's the leading cause. It's not only the leading cause, but it's by majority. But also it's a very nice, interesting system. As a physicist, it attracts me as a very excitable system. So let me explain you a bit about the electricity that produces the contraction. So the cardiac cells are elongated cells, about 100 microns in length, but about 10 microns in thickness. You can consider them kind of like rods. That's the first approximation. They have a membrane that have a resting membrane potential. This is normalized between 0 and 1, but in general it goes from minus 85 to about 20 millivolts. So originally there are rest membrane potential of minus 85. They're depolarized. And that's because there's a membrane difference between the intracellular and extracellular. So you have a cardiac cell, it's a cartoon. You have the separation of the intracellular and extracellular, but a membrane that keeps the potential difference. Now to the membrane, there are some proteins that go across the membrane that produce ion channels. These ion channels allow the flux of particular ions, the particular independent. There are different ion channels for different ion types, and they allow the flux of the ion and change the voltage of the cell. And when the voltage changes in the cell, the calcium inside the cell is released, and the calcium produces the contraction. So mathematically, when we write the equations of motion, they're relatively simple to write because it's only basically it's Ohm's law. For all these currents, you have a current that is given by a potential, and then you have a conductance or a resistance, but the inverse of the resistance we write as a conductance. The problem is that this conductance, how much they allow to go, the resistance of these ions, they open and close at different times and as function of voltage and non-linearly. So this G that I see here for each one of my currents, my type of currents, each G is highly nonlinear. So you have to write equations of motion for this G, and that's where it is very complicated. So there are two things. One is that you have a lot of, is this me? So there's the complication. You have a lot of different ion channels, and for each of the ion channels, you have to write equations for these conductances that are different for all of them. So it can become very complicated to do. I'll show you a little bit of examples later on in the talk. So the electrical signal produces. Should I turn it on?
I think it's coming from
outside. Oh, okay. Okay, so the electrical signal produces the contraction. So the way it works is that the action potential triggers the calcium, that then triggers the contraction. So you have inside the cells, you have myosin reacting. So when the calcium comes out, binds the myosin with the actin and makes the contract. So you have the cardiac cell that contracts due to an electrical signal that changes the calcium inside the cell and makes the cell contract. When we consider now from single cell to space, now we have to couple these single cell equations that we wrote for one cell. Now we have to put them all together as strands and connect them together, and you have an intracellular and extracellular medium that you have to account for, and the propagation through that. So you write them as a cable equation by diffusion. So now you have this term here, which has all the ion channels for all the cells, and now you have a diffusion term here that indicates the dynamics through the coupling through all the cells. This also becomes very complicated because it has the structure of the heart, but also these fibers, they actually have a complicated dynamics, as I show you. Well, then you have this coupling, and you can have a way that propagates through the heart. Now, the structure of the ventricles or the atria in general, too, they're very complicated. So that diffusion terms include this information. But also, propagation along the fibers is 3 times faster than across the fibers. So propagation along the fibers is about 80 centimeters per second, and propagation across the fibers about 20 centimeters per second. So there's a natural heterogeneity between propagation along the axis across. But now, to make life even more complicated, it turns out that the structure of the heart, just to make it contract better, it actually follows geodesics. So you have these fibers; they follow geodesics. So as you form together the ventricle, if you go from outside to inside, from the epicardium to the endocardium, the fibers rotate about 180 degrees. So that gives you an isotropy, a rotation anisotropy of 180 degrees through the ventricles that you have to account into this diffusion tensor. So that's one of the things that makes life very complicated. Now, if you add contraction, like some of the groups here, you guys are experts on that, it actually makes it even more complicated. So you have to account then for a balance equation for the momentum of the system. So you have a passive tensor, an active tensor, and then the hydrostatic pressure that have to balance. So then that becomes a very complicated that affects also the diffusion term. Now, for now, we're going to be only consider just the electrical propagation. The contraction, we're going to consider that is not the driver of the fibrillation. Anyway, so let me tell you a little bit of the problems of then solving these differential equations in space. The electrical signal that you propagate, it changes in a cell very quickly from minus 85 to about 20 in about 5 milliseconds. So they're very stiff differential equations. So you're required to use a time step of 0.01 milliseconds to be resolved in time. In space, it requires that then, for the propagation that you have, it requires a discretization of about 250 microns, or 200 microns in general. The numbers of differential equations that you have to do per cell is to reproduce these ion channels that I was showing you. So you can go to a very simple model, just a phenomenological model. You can use 3 to 4 variables. It's enough to get some overall dynamics. But there are models that are produced by bioengineers that try to account for all the ion channels in the system. And those models, they can have up to 100 variables for one cell. So that's actually, it can make the problem very complicated depending on the model that you use. So the number of cells simulated, you require 200 microns per spatial resolution. So that means that if I want to do a 4 centimeters square piece of tissue, I require 200 by 200 elements times 4 variables, or times 100 variables, depending on which. And then, so you can go between 160,000 ODEs to about 4 million ODEs just to do 4 centimeter cells of 2D. If you use another model, for example, what is called the 100D model that contains 29 ODEs, that means that you require about 10 to the 11 ODEs to solve in 2D. And if you want to do a simulation in 3D, you require 20 trillion ODEs every time step. Every time step, which is 0.01 milliseconds, right? So now you see why you actually require supercomputer to run these things. Now, but the nice thing to us, the thing that is very, very nice about these systems is that because it's just only basically a reaction diffusion system, it's very easy to parallelize. And not only very easy to parallelize, it actually is almost linear in normal processors. So the more processors you dump at it, the faster it will go, almost linear. So this is really great because then just I care, just as long as you get a lot of processors, then you're fine.
Are you parallelizing it along which dimension?
The 3 dimensions. So you have to spatially, yeah. Now, because the heart is actually not completely homogeneous in shape, you have to balance. If you want to do it really correctly, you want to balance how many cells you do for particular. As you discretize the heart, you have to balance the load.
At the single cell level, is there anything going on there?
Yeah. So this is a good point. It actually at some point there's a bottleneck depending on which one is the diffusion. You have the reaction, the ion channels. So the model is very, very complicated. Now you spend a lot of time on the equations for that more than the diffusion. So for the diffusion part, it's very, very linear. For the other one, it's not quite. But now the machines are so fast that actually, as long as you parallelize along, then the reaction part can be done very quickly as well. So, but it can become a bottleneck. It can become a problem with the memory, because you have too many variables. So if you discretize, you have to account for all the amount of memory that you have to account per processor. But so now we're using the nice thing is that you're now using GPUs. You can access it you don't require a supercomputer. Before we used to run on supercomputers, but now GPUs are accessible, so it's much easier. So you can do it locally, and locally, even with one computer, with using a good GPU, you can now run many of the models that are up to 19 variables, close to real time, at least in 2 dimensions. Nowadays, this is from 5 years ago, 6 years ago. So now actually we can go do much better. We can run actually almost some of these ones. The 8 variables almost in real time. Actually, we can run right now. I'll show you an example of running the 8 variable on my laptop faster than real time. We can do so this is an example. Also, we have this the speed depending on the numbers, but I show you what I want to show you is that there are different ways to use OpenGL to use GPUs. You can use CUDA, or you can use OpenACC. OpenACC is a very nice, simple library that you can just, if you have a serial code, you just put it in there, and you can get right away the speed up of multiprocessors. So OpenACC is not as fast as CUDA, but CUDA you can optimize really good. But it still is something that can do very, very fast. There's also differences between Fortran and C. You can do CUDA Fortran, CUDA C. Fortran still is faster than C, even for these cases. What I want to show you is that the problem with using CUDA or OpenACC is machine dependent. And you have to compile it for your machine. And if you use CUDA, it has to be also NVIDIA kind of cards. But you can use other ways to access the GPU of any machine. So one thing is now with HTML5 allows you to interact with GPU with your machine. So you can actually interact with any machine, no matter what type. If it's Linux or a Windows or a Macintosh, you can access the GPU the same way with the same program using something that's called WebGL. So WebGL, the pros is that you don't need to install any libraries. You don't need to compile it, so it will run in any machine. It's operating system independent. You can run directly over the web through your machine, and you can interact directly with the system. Some of the cons is that some of the browsers don't work quite well. Some browsers work better than others. It's not so straightforward to write. You have to use shaders. It's a little more complicated. And so far, it's only single precision. Because WebGL comes from OpenGL, OpenGL is double precision. We hope that actually in the near future will be double precision as well. So let me quickly show you an example of this using something with a WebGL. Mm-hmm. Yes? The performance. It's actually almost as fast as, it's actually faster than OpenACC when you run it like that. So it's still not as fast as CUDA, because CUDA you can actually really find out, optimize for a particular problem and really optimize. Here you can actually not really optimize that easy, but it is very fast. And I'll show you an example. This, for example, this is the Wiener-Reuter model. This model, produced in 1977, was the first model that actually was done in 2D to demonstrate. Before, it was done in 1991 to demonstrate, to find out if actually this type of equations could support spiral waves. So Art Winfrey did it in 1991, using at the time what it was the fastest supercomputer in the world, which it was a Cray in UC San Diego. So he used that supercomputer to run a 400 by 400 domain. It took 400 milliseconds of time. It took 1 hour. Now in my computer using GPU, you're going to see that runs actually much faster than that. It's amazing that you can run. So here, I'm going to stimulate here. Let me that's one of the problems too. When you use the converter to the projector, it delays the graphic cards. So if I run it without the projector, it would run much faster. It actually runs like 10 times faster than this. So you can imagine that this is where you can interact here. This will run. Just imagine it runs 10 times faster. If I take it out from the yeah, I should have used a DM, but my laptop doesn't have a HDMI. So, but anyway, so the point is that these systems you can run it in real time now, in much faster than real time, using the browser. Let me show you. You can actually do now.
Is this fibrillation?
This will be fibrillation. Yeah, it will be multiple.
What's underlying?
Just the dynamics of the system. Just a pure. Is that period doubling that affects, that produces the, so now it's producing the spiral waves.
Oh, I see. There's no non-conductive regions.
Yeah, so it's a spiral wave here. You can see it blocks here, it blocks there, and it will produce. And eventually this will die out. You need a certain, it will be transient. Let me show you actually, you can do actually 2D. You can actually run in my laptop. I can run a 3D now. This is something that has not been done. This is really like we have done it in the last 2 months. So finally, on a laptop, I can run a heart that I can paste. It's much slower here. Yeah, it's a projector. It will run. It will run not as fast as the other one, but still will run. Just take it 10 times faster than this one. Just still. But you can interact. We have a 3D heart that actually I can run on my laptop, and I can interact and we can run using the GPU. So this is a really nice thing about it. Yeah, it's a shame that it's the projector with the thing. Yeah,
You have to drag both displays.
Right. Yeah. So it slows down the one on my computer. So this is simulating a ventricle, a dog ventricle. So this is also the rotation will be a little slower here, I guess. But you can see here so this is the left ventricle and the right ventricle, and then I put a stimulus here, and it's propagating the electrical wave through that. And then you can have the electrical signal propagation of one conduction, but then you can initiate fibrillation. You see the wave going on the other side. So that is just the same way by stimulating. You can stimulate a primary. So this is a good question. Let me show you an example of how these spiral waves actually form. Now that we have the problem. So now, and actually, yeah, it's funny that it delays so much because actually in my phone, actually some of these things, because a phone has a GPU, you can actually run these things on a phone. So you can actually run, this is running 512 by 512 grid points on my phone. It's 500,000 differential equations every time it's then running on my phone. And you can interact with it. And you can do three-dimensional simulations as well. This is a cube. This is a cube as probably a cube. I'll show you a little bit more about what this line gives in 3D. But this is solving 1 million differential equations every time on my phone. If you run this model on a CPU on a laptop, will go slower because this is running in parallel. So this actually has more power as a GPU than a CPU of a single processor. All right. So in addition, before we can continue doing the experiments or the numerical models, we need to compare with experiments. So we need to know that we're doing the reality. So in the lab we do experiments as well. So let me show you how we actually can visualize electrical signal, so we can compare with the numerical models.
Is this not for the faint of heart? No.
Yeah. Well, you already saw a heart, so then. So what we do is do what is called optical mapping to visualize electrical signals in the heart. So it turns out that there, since 1980s, 70s actually, they started to develop these very nice dyes that go into the membrane, and these dyes absorb at one frequency. They can absorb at one frequency and emit at a different frequency. So they fluoresce at different frequency. And the nice thing is that the form of how they interact in the emission changes as function of voltage. So if the voltage changes, the emission that they do changes slightly. So the fact is that they have an absorption spectrum and an emission spectrum. So these dyes, when you put it in the membrane, I can excite them with one wavelength, around 450, for example, and they'll emit at 650. But the key thing is that the maximum will shift as function of the voltage. So this maximum will shift a little bit if the voltage changes. So the nice thing is that as it changes, so you can have, for 1 voltage, we'll have that fixed. I'm doing a little bit large, this is a very small change, but it's enough that you can measure it. It should shift as a function of voltage. So if I put a filter, and I only measure this light, I'm going to see that for 1 voltage, I get 1 intensity, and for another voltage, I get a little bit smaller intensity. So the change in intensity can be, because it's very small, it's almost linearly, so it's linearly related to my change in voltage. So any change in voltage will be a change in intensity in my signal. So again, so this is an example. So it absorbs and excites. So I use, for example, 500, a green light, to excite. Then I put a filter around 600, so I only see the red. And then I can measure. And then I can measure that signal. And then you can get as it shifts. And as this signal shifts, it's going to give me, with the voltage, it's going to give me a signal. Then in this case, it's inversely proportional because it's moving to the left. So you just have to multiply by -1. So this is an example. This is a pig ventricle that is being perfused. It's open. So I put the dye. You can put then illuminate with the green in the 500 nanometers. Then you put the filter around 600. So this is what you see. And any change in intensity will be the change on the signal. So this is the normal action potential that I was showing you that produces. This is the signal that you see on a single pixel. But now the nice thing is that you can measure just only voltage with a microelectrode in 1 point. This way you can measure everywhere in space. And by putting a color, you can put a color to the intensity that you see. You can say, okay, now I can see it in space. So I say -85 millivolts is going to be black, 20 millivolts is going to be red. So this is a right ventricle. This is, right atrium, sorry. Right ventricle, right atrium. So this is a dog heart. So here is the AV node. So this is the natural pacemaker sending a signal through the atrium, making the contract. So now in this case, when you don't see the contraction, you only see the electrical signal. In general, for this experiment, we put a drug that prevents the contraction.
That's perfectly normal.
That's a normal signal. Yeah, that would be a normal signal going through the atrium. So we put a drug that prevents the contraction, so we don't have a motion artifacts that we'll have to decouple later on for the experiments. This is a ventricle, so you see also we're pacing from this part here, so you see the electrical wave propagating through the ventricle.
Is this upside down?
No, it's the apex will be here. So it's just only a little section of the ventricle, but it's cut.
Can you also get the data internally?
That's a good question. So internally, we can put another camera from bottom and top. So from a heart, you can see the endocardium and the epicardium and endocardium surface. Now internally, it's harder because but what we can do that people are starting to do. I have not worked much on that, but you can use different dyes that are more on the infrared. So then you can use different lights and you can use confocal microscopy to try to see along the depth. So you can do it for tissues that are not too thick.
It's getting excited from the bottom up.
Yeah, this is because I put I didn't show it here, but that's an electrode here that is pacing from here. I'm pacing with an electrode. Yeah, this is just a wave that I'm propagating by pacing myself. Sorry about that. So now, this is an example of the spiral waves that I was showing you. So this is a real spiral wave on a pig heart that develops, and then after a few seconds, then it just stabilizes and breaks into multiples and gets a chaos. So experimentally, we can have these spiral waves and the chaos waves. And the main question, one of the questions that we're trying to understand is what produces this destabilization. So one is like the example I showed you with the students, there is a little decoupling. But it turns out that there are many, many other mechanisms that stabilize, and some studies, some had to do with period doubling bifurcations, some had to do with the anisotropy of the fibers, sometimes to do with the negative tension, and once you go into 3 dimensions, you have topological effects, and I'll show you in a little bit, that are also important. But let me show you exactly first how the spiral waves form. The one we did with the students was actually we break the symmetry, but that's actually what happens in cardiac tissue. In cardiac tissue, when you have a cardiac cell, it gets excited, and then it has to come back to rest before it gets excited again. You can excite sooner and sooner, but at some point there's a minimum diastolic interval at which you cannot excite again. The cell has The ion channels have not recovered entirely, they're blocked, and they cannot excite another activation. So the easiest way to think about this is just like a toilet. You have a toilet, you flush, you have an action potential. You wait some time, you can flush again, you have another action potential. The sooner you flush, the action potential will decrease, will get smaller and smaller. But there's a point at which you cannot flush anymore. You have to wait to fill a little bit. So there's a clear refractory period. So when that happens is that if I have a wave and I stimulate behind the wave, if the tissue is completely excitable, then I have a target wave that propagates behind the original wave, right? So this is my wave. I stimulate, and then I have a target pattern. Right? Now, I can do the same thing, but if I stimulate too early, when the tissue is refractory, that activation is going to die. It just dies out, right? Because it's too early. Now you can imagine I can do now a time in between, right? That part of the tissue is excitable, but part of the tissue is refractory when I put the stimulus. So it will propagate in one direction, but it will block in the other direction. So that actually breaks the symmetry and starts doing the spiral waves. That's what we did with the students. We start with a broken pulse that propagates in one direction, but it was blocked in the other direction the first time. So this is what happens, right? You have a wave, you put a premature stimulus, it propagates in one direction, but it blocks on the other one, so it breaks the symmetry and initiates the spiral waves. So that's what I was doing on the simulation, on the real simulation. I was putting one stimulus and another stimulus just next to it behind that broke the symmetry and produced. So when you have a spiral wave, we tend to think spiral waves like that, like Archimedean spiral waves with a circular core. But it turns out that there's different dynamics depending on the wavelength and the excitability of the system. The tip trajectory, how it turns, is defined by the wavelength and also how quickly you can excite neighbors, given the curvature of the spiral wave. So by changing parameters on the models, you can actually change the dynamics of the waves. You can go from circular core to epicycloidal trajectories. You can go to cycloidal trajectories. You can go to, now instead of outward petals, inward petals, outward petals. You can go what is called hypermeander, so more complicated dynamics. And in the case when the wavelength is very high or very excitable, then you get up to what is called linear cores. So it just turns very quickly, but it blocks by itself, and it turns again and blocks by itself. So all that dynamics happens as you change parameters, but those parameters can be related to physiology. So for example, the excitability, how much oxygen you have in the system can go from here to there. So when you start the spiral wave in the heart and the heart starts going slower and there's not enough oxygen being depleted, then you go from very high excitability to low excitability into that. So the trajectory of the spiral waves changes as function of physiology.
Those trajectories, do those trajectories have any clinical?
Yeah, because let me show you that. Yeah, so here, let me show you an example here. I have a spiral wave. So this one was a spiral wave formed actually by depleting some of the oxygen in the system or by changing the wavelength. So if you put a pharmaceutical that changes the wavelength, you put a drug that enhances or suppresses, it can change the dynamics of these when they form. So that's one of the ways when they form, and this is an example of a linear core trajectory. So when spiral waves form in the heart, you can have them both in the atria or in the ventricles. When they happen in the atria are receiving chambers, so it is not deadly. It can affect your way of life, but it's not deadly. When it happens in the ventricle is the one that pushes blood to your body. So that if you have spiral waves there, then you actually die within minutes. So in the atria, when you have them, there's almost to defibrillate with chemical drugs. So that's when you can put the different drugs that actually can change the dynamic of the spiral waves, so they can actually disappear in time.
So I meant the previous slide. If those were all in the ventricles.
Oh, they can happen both ventricles or atria. And in general, in the ventricle, because they destabilize very quickly, they go from there to right away to multiple waves. Mm-hmm. But also, depending on their trajectory, they can fit more or less into a ventricle. Mm-hmm.
So you said that the circular core occurs often when there's not enough oxygen in the system.
Mm-hmm.
But we also know that the spiral waves are faster than the normal pacing of the heart.
Mm-hmm.
So could the circular core appearing cause the heart to beat faster, which means oxygen will ends up being pumped faster because of that? Because there's a
at the beginning will go faster, yeah. But when you have multiple spiral waves, then that's when you stop producing, and then. So now the problem is that now how you go to 2D to 3D. So how do you visualize spiral waves in 3D? In 2D it's easy because you have X, Y, and a color for the voltage. In 3D you have X, Y, and C, but you have a voltage that is hard then to see for a color. So in 3D you cannot really, you have to choose a contour or something like that to look in 3D. Another option is that the tip of the spiral wave identifies very well the dynamics of the spiral wave where it rotates. So when you go from 2D to 3D, you can imagine tracing at different planes the tip of the spiral wave. So then in 3D, a spiral wave becomes a scroll wave, which can be defined by the vortex filament. So instead of a vortex point, you can have a vortex filament in 3D, and by calculating the torsion, the twist, and the curvature, you know everything around the dynamics of this spiral wave in there. So, but now again, now you have 3D, now you have yet another emerging behavior that you can have. You can have the vortex filaments, they can be lines, but they can actually fuse themselves and form rings. So you can have vortex filaments that go from surface to surface, or they can bend and go from one surface to another surface, or they can bend itself and then become rings. And once you have that, you have a lot of topological effects. You can have, let's see if this plays. Yeah. So you can have a conduction block that produces a ring that appears and disappears. But you can have a conduction block that then appears and then fuses, it has the right phase, it fuses with the other one, or vice versa. You can have one element that then elongates too much, pinches off, and then produces another vortex filament. So now it becomes really complicated. In addition of the other mechanisms that exist, now you have also topological effects that can dynamics in 3D. So this is a simulation in 3D of the. So this is this is what you were talking about. We cannot see inside the heart, right? It's hard to see. So this is what optical mapping will just show you the surface. So it will be a heart from the top, the bottom. I mean, from the front, from the back, from the view from the apex. And this one will be a transparent view where you can actually see the vortex filaments. So numerically we can do it. We can visualize the dynamics inside the muscle, but not just only the surface. In there. All right. Okay. All right. So now once we have the spiral waves, in addition of studying how we initiate them, what are the mechanisms, we try to study the mechanisms that terminate them. So how do they defibrillate them? So in general, when they happen in the ventricle, the only way you can do it is with a big shock. You have to defibrillate by an electric shock. And in general, in order to terminate that, so this is what you do. So let me start the movie again. So you have spiral waves. You put an electric field that's going to excite all the cells and get them all excited, and then that terminates the arrhythmia. So you have the multiple spiral waves there. You have electric shock enough that excites all the cells and then comes back to normal. So in order to do that in a heart, you have to go through, even if it's internal or external, you have to go through all the cells. You have to put an electric field that's strong enough to excite all of them. It turns out that you require about 5 volts per centimeter to excite cells. And that transforms, if it's internal or external, it can transform about 30 to 45, 100 to 360 joules, which is 1,000 volts times 30 to 45 amps, which is a lot. This is very, very strong. And if it's internal, you can go to 7 joules, but still 7 joules is a lot. Even the amount of energy you require to move a muscle is 0.01 joules. So 7 joules is a... So if you have an external defibrillator, the pads, like you put them in here and then you shock, you have to go through the whole chest and all the organs. So it requires 100 joules. Internal, you can put in the clinic. You can have catheters inside the heart. So those are just or an ICD. Yeah. So when you have the catheters inside, then you only have to go within the heart and require 7 joules. But even the 7 joules still is very painful. So we're trying to figure out that not only is painful, but also can produce damage to the tissue. This is how the heart, after being defibrillator, he has a lot of this hemorrhage coming from there. So we're trying to figure out better methods to defibrillate. So the way actually defibrillation works is very interesting. The heart is not very homogeneous. It has a lot of heterogeneity. It has gap junctions, but it has also a lot of vessels as well. And this is only just a picture of the not the veins, but the arteries. So this is just the arteries. I fill it up with a microfill and took a fill. So this is just half of all the heterogeneities that you see by vessels and the rest in the heart. But it turns out when you put an electric field, if you have a homogeneous system, you're only going to excite the boundaries. So if the heart was completely homogeneous and you put an electric field, you will only excite the boundaries and that's it. So everything that is inside the heart will not get affected. So you will not be able to defibrillate. But the fact that we have all these heterogeneities, every time we have a hole with a pieces of other pieces of tissue that are just gap junctions or extracellular metrics, but in particular the vessel distributions, the vessels have blood that have different conductivity. So when you have an electric field and you have different lines of the lines would change, and it basically it's just a different conductor. So you're going to put charge at the boundaries of these heterogeneities. So once you have charges at the boundaries, if the charges accumulate higher than the threshold, they can produce an activation within inside the tissue. So that's actually how the defibrillation works. If you have a piece of tissue with a lot of heterogeneities and you put a shock, then you can excite within those heterogeneities. The current goes in and out, and it can actually produce an activation inside the tissue. Now, how many inside the tissue sections you can excite, it depends on the electric field, because it depends on the sizes of these heterogeneities, right? If it's a very small electric field, only the largest heterogeneities are going to get excited. If you get as you go higher and higher electric field, the smaller heterogeneities can actually have more charge around the surface, and they can get excited. So this is an example with a higher electric field. You excite more inside. That's why when you have the multiple spiral waves, you require a very strong electric field so you can excite everybody inside. You can all these heterogeneities enough to excite. So the idea is that instead of using one big shock, if we use multiple shocks just to slowly change the arrhythmia from one type to another different frequency, we can try to synchronize the system and terminate the arrhythmia. So this is the method we defined. So we decided to, this is just some of the fixing the height. So the idea was that if you have a system with spiral waves, if you do multiple shocks but with lower energy, you're not required to excite all the tissue at once and terminate it. You can just little by little excite the cells and then recruit some of them to a different frequency. So you start having more and more to recruit this new frequency, and then until everybody's synchronized, and then you stop. So this case actually, when we did the simulations numerically, it turns out that it was very effective. We can almost terminate almost all the time with 90% the energy. So then we went experiments in vitro. So we did experiments in atria. So we had the in vitro experiments with the spiral waves. And we do the one shock. So this is going to show a spiral wave with one shock that is close to this shock, the threshold that I was telling you, 5 volts per centimeter. This is 4 volts per centimeter. So this one actually is going to fail. So this is one shock, about 4 volts per centimeter. It almost excited the whole system, but it failed, right? So the one little section remained and restarted an arrhythmia, right? Now, we'll do it again, but now with 4.6 cells, this is almost 5 volts per centimeter. And in this case, it terminated the arrhythmia, right? It was strong enough. Let me show you it again. So you have that spiral waves. And the one shock, and it terminates. All right. Now, let me show you the case with the shock. It's just only a few milliseconds. So it's a biphasic shock of, it was 4 milliseconds.
4 milliseconds.
Yeah. Mm-hmm. But it's very strong. Now, these other shocks are also 4 milliseconds, but each one is much smaller. So again, this is 0.9. So this is from 4 volts per centimeter to 0.9 volts per centimeter, right? Now the energy goes as the square of that, right? So then this is a 10% reduction. So here's going to be 1, 2, 3, 4, 5. It came back. It almost terminated. It almost synchronized the system, but not quite. So let me go a little bit more, 1.4. And it terminated then you have it was just an SA node activation at the end. So it terminated. So one of the things you can characterize this is by calculating the amount of tissue excited as function of time. So when you have an arrhythmia, the amount of tissue is oscillating. When you defibrillate, you have to excite all of them, right? So then all the tissue gets excited and then terminates. Now, if you take the derivative of this signal, it tells you how synchronized the system is. So it tells you that when the one shock, everybody got excited, but not at the same time, right? So the shock was strong enough that everybody gets excited, but not. It took their time to everybody reach that value, right? Now, in the case that we almost got it, you see, with every shock, we were getting a little bit more and more tissue excited, but we didn't get all the tissue excited at the end. So, and it was starting to grow the synchronization. In the case that actually worked, we actually have that at the last one, we actually we excited all the tissue. So little by little, we synchronize the system to this new frequency.
Wait, are you talking about leap here or
The leap, yeah. So the leap was synchronizing. The non-leap, the one shock is not.
two are
Yeah,
non-leap.
yeah. This to a leap.
Oh,
This
those
to the leap, right? The leap.
Oh,
So
I
the
see your arrows.
yeah.
I'm sorry.
So the leap is synchronizing, and the other one is not synchronizing. All right. So the mechanism is different, right? So the mechanism for one shock is just excite everybody, but you just have to put enough muscle that everybody eventually gets brought up. The other one, use little pushes, that little by little everybody synchronizes to this frequency, and then you let it go. All right. So then we went once we tried it in vitro, then we went in vivo, and we tried to. So we tried like in the clinic. So we have these are the catheters that you put in the clinic. You put in the atria. So this is one in the right atria, one in the left atria. And yeah, for the atria. Now this is a view then of the in vitro with the open chest. So this is the head is here of the animal. The legs are there. This is the ventricle. This is the atria. This is the right atria. We have fibrillation in the atria. So this is going to be fibrillating and driving the ventricle a little complicated, but this is the fibrillating atria. We're delivering one shock that is strong that is going to terminate the arrhythmia. So you remember, for human, it's about 7 joules to defibrillate. This because it was a smaller animal. It only required 1 joule to defibrillate, but it's still 1 joule just so that it was enough to defibrillate, but also it's big enough that recruits all the nervous systems, and then you see the jumping of the animal, right? That's why it's so hurt. That's why it hurts so much when you deliver these pulses, because the heart doesn't have nerve, it doesn't feel, but the body feels the electric field, and it's such a strong electric field that they need recruits, and then just make you jump. So let me show it one more time.
This is a deceased.
No, this is we can induce clinically an arrhythmia. So it's a normal, but we induced an arrhythmia. Now, okay, so here's the view of the heart like that. Yeah, so this is the way it was. So now we'll do the same thing, but now we're going to use 10% of the energy, but 5 pulses. So it terminated the arrhythmia too, but now in this case there was you see was very little, so the whole body didn't jump, right? The whole body was Rex in step. What is the? Oh, this is the lung. So we did that actually in 7 different animals, and it turns out that actually it was very, very close. Both the average energy reduction was 10%, was only using 10% of the energy compared to the one shock. This in some of the experiments we did it. We took the animal at the end, and we did both experiments in vivo, but then in vitro again, and did experiments both with the optical mapping and didn't match exactly. The frequency was similar, and the energy required to do it in the clinic or do it in vitro, where we're looking actually at the spiral waves, it was about the same. So I hope I show you here that a couple of things. One, the heart is a very complex system that is meant to oscillate, but because systems that oscillate can go out and have much other dynamics, it can have these other dynamics that in this case are dangerous. We can use computer simulations to try to study the dynamics, and in this case, we started with computer simulations to try to create a method that we could try to use, that we developed it in vitro, and then we eventually did it in clinical, and it works at least for animals. We haven't gone through larger animals or human, but I think it's a good example of how these computer simulations can help in real life. And then I just want to thank all my collaborators, especially Elizabeth Cherry, my wife, who works with me for many years. She's also a math professor in Rochester Institute of Technology, and so my group. And if you have any questions, you can always send me an email. And thanks so much for your attention.
Thank you, Flavio. That was a spectacular talk. Are there any questions?
Any questions about the...
I have a question. We know that in the case of VFib, that we need to defibrillate because otherwise the patient will die, right?
Yeah.
Yeah. So we also know that in all of these cases where we're trying to correct for fibrillation, we need to send either one pulse or a series of pulses enough to restart well, first off to clear out and then restart the electrics of the entire system. Is it the case that the patient reaches like clinical death before the system just ends, like loses all of its energy to begin with?
Yeah, no, that's a good question. Yeah.
Because otherwise you would only have to stimulate at the same like initial point, I guess, the natural pacemaker in the heart in order to propagate a wave, right? You wouldn't need to stimulate the entire system.
Yeah. So the question that I think you're asking is that there's a particular time when actually you can defibrillate that works, and actually you've seen in the movie sometimes they bring the patient into the IC and then they start trying to defibrillate and they say no, we declare that it doesn't work, right? It's because as you start having this the arrhythmia, the heart stops sending blood, so then the oxygen starts to be depleted in the system, so the excitability of the system starts to decrease. So the spiral waves still remain there, but it's very hard that as excitability decreases, it's harder to excite the cells with an electric pulse. So that's why, so actually it's called Wigger stage 1, 2, 3. As a fibrillation starts, it changes the dynamics and it changes in time very quickly from one stage to another. And so not all fibrillations are the same. They start at different times. That's why the sooner you come and defibrillate someone, that's why they have now all these defibrillators almost everywhere, because it's very easy to defibrillate someone, but as soon as you do it very quickly. If you do it as soon as it starts, there's enough excitability in the system that the shock will work. The longer you wait, the less excitable it is and the harder it is to defibrillate. And that's because, yeah, the excitability keeps changing. So when it's very, very low excitable, no matter how much current you can put as much as you want, you're not going to excite anybody. So that's it.
What is the path to commercialization of LEAP?
Oh, it's a long one.
Oh, that's not good.
Yeah. Because there are two things. It is, but it needs to be tested. That is real. So companies right now, they have methods to defibrillate, and it works. So they don't want to. If it works, why mess it up, right? As long unless so, you have to prove first that it's really, really low enough that it's very painless, painless, really. So one thing. The other thing is that it's always reliable. The problem with LEAP is that, at least for the ventricle, will be always work because you have to bring it back alive, right? But for the atria, when you do multiple shocks, you can do a shock when the ventricle is being activated. And when you have a shock when the ventricle is activated, you can actually initiate an arrhythmia in the ventricles.
So I don't understand why you would be, you said earlier you don't worry about AFib.
No, but if you, I mean, you're worried to, LEAP will be a good option for the fibrillation of the atria.
So what about just ventricle?
Yeah, for ventricle, yeah. So ventricle LEAP will be a good try to do it.
So what about that
Yeah.
path to commercialization?
That part of commercialization, yeah, you have to still show that then that low energy when you go through. We have done it on in vivo, but intracellular. I mean, inside the heart, not extracellular. So I don't know yet when you go through the whole muscles how much low energy will you need to repair.
For ICD. Technology.
Yeah, for ICD, yes. So that you can probably try to put it there.
But you don't know of any one trial?
No, we have some. We have the patents now, but still we're still trying to figure out. But we've been working more on the atria more than the ventricles, because for the ventricles too, the catheters that we have, they're not big enough to produce an electric field that is homogeneous enough to excite all the ventricles. So we tried on the ventricles. These examples are showing the atria. The ventricles, we can reduce the energy, but not to 10%. We succeed to defibrillate, but about 50% the energy. So 50%. So those electrode catheters, we need to put them in a different location or different shape or different forms. So now the simulations, the models with simulations is hopefully we do with Jim and Gil. That's what we're trying to see, figure out how to lower even more the energy if we can make them better to do it in that direction.
Could you comment a little bit about the possibility whether or not you are planning to couple this electrical model with a mechanical?
Yeah, so I have done a little bit, so like there's a movie there with a little contraction. So I have done a little bit of that, but the thing is that most of the studies that I'm interested are due to the electrical signal developing the problem contraction. When you have a model of electrical contraction, as Jim was mentioning, just contraction and electrical will not give you much information of many dynamical problems in the heart. You have to include the fluid dynamics as well. So now you're talking about putting the three systems together, which is even more complicated, right? Because now you have to really solve the Navier-Stokes with the pressures to give you the right pressure at the boundaries that gives you the right pressure for the contraction and then for the electrical. So you have to do the three, and that's going to be really takes a lot of effort just to study some of the, then what would happen when you have the whole heart. So, yeah, it's...
What's interesting for me in that situation is that the chaos is absolutely beneficial and necessary in the fluid case, as opposed to being life-ending in the electrical case. Right? You need turbulent flow.
Yeah, I mean,
we all have turbulent flow in our heart. Right?
So some of the simple studies that you could do, but still it has to include some of the fluid. It's just the structure. You saw how the heart is actually very smooth from the outside, but in the inside you saw that picture of the open heart that I had for that it was very it has a lot of what is called pectin muscles. It's very complicated. It's because when it's the fluid inside the heart, you want to make sure that all the fluid basically goes out, that doesn't stay there, because then it will actually form from clots. So you want the fluid inside the ventricles and the atria to be chaotic, to really be mixed well and not to remain there. So those the contraction and the shape of the inside of the cavities is crucial to make the dynamics of the fluid chaotic. So that's one of the studies that could be done for that effect.
It's interesting how it's polar opposite, right? You want chaos.
Yeah, in that case you want chaos. Yeah, good mixture. Yeah, but I mean, so it's an interesting. I mean, from a mathematical point of view and computational point of view, it's very interesting to try to couple the three together. But it's very hard, and so you need money to do. You have NSF or NIH money to do that, and but then in order to do that, you have to have an answer. You have to say what problem you want to solve. So you cannot just do and go say, well, I want to do it because we need to have a model for that. So it is. But I hope at some point eventually different groups combine and they can actually combine together. Because also the problem is that it's not only the electrical signal, the calcium signal that I was mentioning, it's also when many models we put the calcium, but the calcium system itself is very complicated. There are groups that just only work on pure calcium dynamics. So even the calcium dynamics is not completely well done, well understood. There are no models that are completely well done for calcium, which is the one who drives the contraction. So it's a still, I think we're very far from a realistic model that can actually be combined together that actually will give you a realistic. I mean, you can give a model that will look like a contracting that is doing the right thing, but to make it actually physiologically correct, still but we have to do it at some point. Yeah.
Would it make sense to use the simulator to search for interventions?
Yes. So that's the now that we can do simulations in close to real time. Now we're closer to do patient specific. So the idea is to get structures of because the dynamics also changes depending not only the physiology but also the structure of the patient. So there are groups. There's a group in Johns Hopkins that is using three-dimensional structures of patients to know where to actually ablate. So one of the cases you have not very often happens that you have spiral wave tachycardia in the ventricle that is stable, and that's because sometimes the tissue is not. It has some already dead tissue. You have a previous heart attack, so parts of the tissue is dead. So you have scars where the spiral waves actually anchor, and when they anchor, they don't break. So then you have constant tachycardia, but not fibrillation. So those ones, they try to go there and ablate and cut and then try to see where. So that's where actually these numerical simulations can help on decide where to cut and do the simulation of the spiral wave and see where is the best place to cut or terminate the spiral wave.
So in that sense, would it be possible to define the space of interventions and you have your criterion of optimality and then
Yeah, and then you can tell and the nice thing, especially now that you can do it, you can do relatively quickly CT scans of a heart of a patient, then go put it in the simulation, do see, and see, okay, and tell the clinician, I think it's better if you do here than here. Yeah, so hopefully that would, yeah.
So the second grant you have listed there is the cybercardia grant, although I think the number is...
We have different numbers. Each one has a different number.
Grant. That's cybercardia.
Oh, sorry, yeah, that's probably, yeah. There's the frontiers, yeah. Yeah.
But what I wanted to say, again, for LEAP and ICDs currently apply the 7 joules, I guess.
Mm-hmm.
And they have to decide when to deliver these 7 joules. And the only information they have are two leads into the heart, plus the third lead, I guess, is a...
So they have a third one, yeah.
Third lead. So you get 3 signals into the device, and it runs a so-called discrimination algorithm, trying to decide if this is a life-threatening arrhythmia or something in the atrium, for example. That, as you said earlier, is not life-threatening. So if it's in the ventricles, it needs to deliver the shock. But they are always extremely conservative, these algorithms, because you can never have a false positive because the patient dies if you don't deliver the shock and there's VFib. But if you have something supraventricle, like AFib, it'll still sometimes deliver a shock.
The shock when it's not.
These are called unnecessary, or there's another word for it. Anyway, they're false negatives, basically.
And they're very painful, and that's why...
and as you said, they cause damage to the...
yeah, but more than the damage for those ones, actually, more patients that have it, because it's so painful, and they're very... So not everybody gets these discharges, but people who sometimes get these false positive, the discharge is so painful that they, at some point, they say, take it out. If I'm going to die, I'll die, but I don't want to have it. They're always worrying when it's going to happen, and it's so painful that they just... So that's a deterrent for people to use the ICDs, and that's one of the things that if we can fix that, then that probably allows more people to have
these
ICDs.
Algorithms in these devices have to make these life decisions and life quality decisions as well in a very short time frame.
Right.
And with limited information currently.
Yeah, so doing the numerical simulations with these systems hopefully will help identify when they fail, these algorithms, right? Jim?
Here's the question. I don't know if you know the answer, but I don't know whether the pain from the shock is on a linear or a logarithmic scale. So if you cut this strength by 10, Are you cutting the pain by 2 or are you cutting it by 10?
Yeah, that's one of the things. Pain is actually a pain to quantify.
What?
Pain is a pain to quantify.
Yeah.
It's very hard to
Well,
quantify.
many
It is,
many
but
perceptual things are really on a log scale.
but even one of the things that, for example, people have shown that when you have multiple shocks, even if the second or third are lower, they still feel it more. Once you have the first one, they feel that the next one they actually they feel it more, even when you lower the energy. So it is hard, and so it depends. And people have different thresholds. They say that redhead people have a very low threshold for pain compared to others. They have some numbers that they have done. It's very, very difficult to quantify. It seems like it's below 1 joule, but they don't know exactly how much. And again, where probably also where the electric shock is done is if you get an electric shock in your leg or you have it on your arm, it's different, right? Or when you have it here, sometimes different sections are more they have more nervous systems and more nerve receptors than others. So it's a very complicated. So I don't know the answer. I know that it's very hard to do.
Any other questions for Flavio? Thank you so much.
All right, thank you guys. Thank you so much.